sounds, well, almost trivial. Empty space.
Right, what's there when there's nothing there.
Exactly. The old view is pretty clear. It's just emptiness, a void.
But modern physics tells a very different story. It's looked much closer.
And that's our mission for this deep dive, isn't it? To look at the sources you brought and see why physics now views empty space not as nothing, but as something dynamic, active, almost buzzing.
That's the plan. We're talking quantum fields, vacuum energy, these weird virtual particles, space-time itself playing a role.
And yeah, the whole dark energy mystery, plus this massive cosmic puzzle everyone's talking about.
Okay, so let's set the scene. Classically, a vacuum was just the absence of everything. Matter, light, gone.
Truly empty. Inert. Nothing happening.
Makes sense from what we see day to day.
Totally. You pump the air out of a jar, it feels empty.
But then quantum mechanics and general relativity arrived, and they flipped the script. Quantum field theory, QFT, is key here. It's our best description of fundamental particles and forces.
And it says reality isn't particles in space, but fields filling space.
That's a great way to put it. Think of an electron field, a photon field, permeating everywhere.
Like invisible oceans covering everything.
Sort of, yeah. And particles, they're just excitations, like ripples or waves in these fields. An electron is a ripple in the electron field.
Got it.
But here's the kicker for empty space. Even when these fields are in their lowest energy state, what we call a vacuum, no real particles around, then they're not. Still, they're not quiet.
Hold on. How can nothing be not quiet? How can it have energy if there are no particles? That sounds paradoxical.
It really does. It boils down to Heisenberg's uncertainty principle.
Position and momentum, right?
Well, yes, but it also links energy and time. You can't know the exact energy of a system at every single micro instant, meaning over tiny fractions of a second, energy has to be uncertain. It can fluctuate.
So even supposedly empty space can't just have precisely zero energy. It has to sort of shimmer.
Precisely. This built-in unavoidable energy jitter is what we call zero-point energy, or ZPE.
0 point. Okay.
It's the absolute minimum energy a quantum field can have, even at absolute zero temperature in a perfect vacuum. It's the ground state, but it's dynamic, not static.
And this is where virtual particles come in, this background buzz.
Spot on. These energy fluctuations allow pairs of particles and antiparticles, virtual photons, virtual electron-positron pairs, to momentarily pop into existence.
Hop up from nothing.
They borrow energy from the vacuum, exist for an incredibly fleeting moment, then annihilate each other, paying the energy back.
Wow.
They're virtual because they're so short-lived they don't follow all the rules of real, stable particles. Like quantum ghosts, almost.
Okay, that sounds incredibly theoretical. Is it just maths, or is there actual proof this is happening in empty space?
Oh, it's much more than maths. We have real, measurable effects. The Casimir effect is probably the most famous.
Ah, the plates. I've heard of this. How does nothing push metal plates together?
Okay, picture two perfectly parallel, uncharged metal plates really close together in a vacuum. Outside the plates, the vacuum is fizzing with virtual photons of all possible wavelengths. But between the plates, it's constrained.
How so?
Only virtual photons whose wavelengths fit neatly between the plates can exist there. Like harmonics on a guitar string, only certain notes fit.
Okay, so fewer types of virtual photons are allowed between the plates.
Exactly. Fewer virtual photons popping in and out means less quantum activity between the plates compared to outside. This creates a tiny pressure difference.
Pressure from virtual particles.
Yeah. More pressure from the outside pushing in than from the inside pushing out. The result: a measurable attractive force. Predicted by Casimir, verified experimentally. It's the vacuum pushing.
That is genuinely mind-bending. Nothing exerting force. What else?
Another big one is the Lamb shift. It's about hydrogen atoms. Physicists measured the energy levels of hydrogen very precisely. They found a tiny difference between two levels that, according to simpler theories, should have had the exact same energy.
A slight mismatch.
A tiny but definite shift. And the explanation: the electron in the hydrogen atom is constantly interacting with the vacuum fluctuations around it, those virtual photons again.
So the empty space is sort of jostling the electron.
Kind of nudging it, yeah. Affecting its energy levels just slightly. It's like the electron feels the vacuum isn't truly empty.
Like background noise affecting something.
A bit like that. And even more precise is the anomalous magnetic dipole moment of the electron.
Okay, that's a mouthful.
Yeah. Basically, electrons act like tiny magnets. Their magnetic strength is slightly different from what basic theory predicts.
And the difference comes from?
Interactions with virtual particles in the vacuum. When you calculate the electron's magnetic moment, including these vacuum interactions, the result matches experimental measurements to an absolutely staggering degree of precision, like 10 decimal places or more.
Wow, that level of agreement. That's powerful evidence.
It really is. It tells us this vacuum activity is real and has consequences.
All right, so empty space isn't empty. It's got this fluctuating energy, virtual particles zipping around. But you also mentioned other fields just being there, like the Higgs field.
Yes, the Higgs field. It's another fundamental piece. It's thought to permeate the entire universe, everywhere,
And its job is?
giving fundamental particles mass.
Hmm.
Without the Higgs field, particles like electrons and quarks would be massless, like photons just flying around at light speed.
So particles get heavy by, like, interacting with this Higgs field.
Think of it like wading through treacle or maybe pushing through a crowd. The more strongly a particle interacts with the Higgs field, the more resistance it feels.
And that resistance is what we perceive as mass.
That's the idea. Photons don't interact, so they stay massless. Electrons interact a bit, top quarks interact a lot.
The stickier it is to the Higgs field, the heavier it is.
Got it. And crucially for this discussion, the Higgs field is special. Even in its lowest energy state, the vacuum its value isn't zero. It has what's called a non-zero vacuum expectation value.
Meaning it's always on, everywhere,
Yeah.
even in totally empty space.
Exactly. It's always there, a fundamental property of the vacuum itself, ready to give mass to particles passing through.
And finding the Higgs boson particle at CERN.
That was finding the excitation, the ripple in this field. Huge confirmation.
Incredible. Okay, so we've got fluctuating energy, virtual particles, a mass-giving field. What about space itself? You mentioned space-time isn't just a passive stage.
Right. Now we shift gears slightly to Einstein's general relativity.
Gravity is curved space-time.
Exactly. Gravity isn't some spooky force pulling things. It's mass and energy warping the fabric of space-time. And space-time itself isn't just a background. It's dynamic. It can stretch, ripple think gravitational waves.
So the space between stars isn't just distance. It's an actual thing that can be affected.
It's a thing with its own properties, its own geometry. It exists even if you take all the matter and energy out. It's fundamental.
And this idea of space having its own properties, does that lead us to dark energy?
It does. This was the big shocker from 1998, looking at distant supernovae.
The universe's expansion is speeding up.
Yeah, accelerating, not slowing down like everyone expected gravity would make it do.
So something's pushing it apart.
And the leading idea is dark energy, some mysterious energy inherent to space itself. As the universe expands, you get more space and thus more dark energy, pushing it to expand even faster.
And the simplest idea for dark energy is it's just the vacuum energy, the zero-point energy we talked about earlier.
That's the most natural thought, yes.
Yeah.
That the inherent energy density of the vacuum acts like a sort of anti-gravity, negative pressure.
So it ties back to the quantum vacuum fluctuations.
It's often linked to Einstein's cosmological constant lambda, a term he put in, took out, but now it's back as possibly representing this intrinsic energy density of space.
Okay, that sounds neat. Quantum vacuum energy explains cosmic acceleration. It all fits.
It would fit beautifully, except...
Uh-oh. There's always an except in physics, isn't there?
This is arguably the biggest except of all. It's called the cosmological constant problem, or, more dramatically, the vacuum catastrophe.
That doesn't sound good.
It isn't. If you take quantum field theory, our best theory of particles and fields, and calculate the expected energy density of the vacuum from all those zero-point fluctuations,
Just get a number.
you get a number, and that number is about 10 to the power of 120 times larger.
Wait, what? 120 orders of magnitude larger?
Than the value of dark energy we actually observe from the universe's expansion.
That's not just wrong. That's spectacularly astronomically wrong. That's like measuring your height and being off by more than the size of the galaxy.
It's considered the worst theoretical prediction in the history of physics, by far.
So if the vacuum energy was really that huge,
The universe would have either instantly ripped itself apart or collapsed into a singularity nanoseconds after the Big Bang. No stars, no galaxies, no us. Nothing remotely like what we see.
so our fundamental theories of the very small and the very large clash catastrophically when it comes to the energy of empty space.
That's the heart of the problem. It screams that we're missing something profound about how quantum mechanics and gravity work together, especially concerning the vacuum.
Are there any ideas how to fix this?
Oh, plenty of ideas, none proven. Maybe there's some deep unknown symmetry, like supersymmetry was hoped to be that makes almost all of this energy cancel out perfectly.
But we haven't found evidence for that symmetry.
Not yet, not where we expected. Then there's the anthropic principle.
The idea that we just happen to live in a universe where the value was small enough for us to exist, implying maybe countless other universes with different values.
Exactly. Controversial, hard to test, or maybe general relativity itself needs tweaking on cosmic scales. Or perhaps dark energy isn't constant vacuum energy at all, but some other changing field, quintessence.
So, a huge puzzle with lots of potential paths, but no clear solution yet.
Not even close. It's arguably the biggest unsolved problem in fundamental physics.
And related to these extreme quantum effects. What about space-time foam? That sounds wild.
It is wild. It's a theoretical idea from John Wheeler. He wondered what space might look like at the tiniest possible scale, the Planck length. That's 10 eurometers, unimaginably small.
Okay.
Down there, the uncertainty principle might make quantum fluctuations so violent that space-time itself isn't smooth anymore. It might become chaotic, turbulent.
Foamy.
Exactly. Constantly bubbling, warping, maybe tiny wormholes or black holes popping in and out of existence, like the virtual particles, but for geometry itself.
Wow. So the fabric of reality could be this churning quantum mess at the bottom.
That's the picture.
Yeah.
But to really describe it, we need a theory of quantum gravity merging quantum mechanics and general relativity. That's the holy grail people are chasing with things like string theory or loop quantum gravity.
So this is all very much cutting-edge, active research then. It's not settled science.
Far from it. You've got huge telescope surveys like Euclid and the Roman Space Telescope trying to pin down dark energy's behavior. People are doing ultra-precise lab tests of the Casimir effect. We're listening for gravitational waves to test GR. Theorists are banging their heads against the cosmological constant problem and quantum gravity.
It's a massive frontier.
Absolutely. We're constantly probing the edges of what we know about space, time, and the vacuum.
Okay, let's try and pull this together for you, our listener. That simple idea, empty space. Turns out it's not simple, and it's definitely not empty.
Not by a long shot. It's a fundamental stage, buzzing with quantum energy fluctuations, filled with fields like the Higgs, woven from space-time fabric itself, and maybe driven by this mysterious dark energy.
It completely changes how you think about the space around you, or the vast voids between galaxies. It's not passive nothingness.
It's active, dynamic, and holds some absolutely enormous secrets.
Yeah, it really makes you reconsider what nothing even means.
And maybe how much of reality is just hidden from our everyday view.
Which leads us to a final thought for you to chew on. That cosmological constant problem, that 120 orders of magnitude mismatch. If our very best theories are that wrong about the energy of the most basic thing imaginable, empty space, what fundamental piece of the puzzle are we missing?
What unknown physics could be operating right under our noses, ensuring that almost all of that predicted energy just cancels out, allowing the universe and us to exist?
Solving that could rewrite everything we think we know about reality.
It really could. Maybe the emptiest parts of the universe have the deepest stories to tell.
Thank you for joining us on this deep dive into the surprisingly full nature of empty space.
Keep asking questions.
We hope it gave you something fascinating to think about. Until next time, keep exploring.